If my little picture in the bottom right corner is in the way, just let me know. All right. Now I'm going to. It's been a little while since I've done notes this way. Okay. So bear with me. If I go a little too fast and flip the screen before you have a chance to write it down, it's not like at home where you can hit the pause button. Okay. Just raise your hand a little bit, and that'll signal to me to either go back or wait a second. Okay. But I try to talk in enough amount of time that allows you to write down what you need to write down for each slide. Okay. So far, this year, we've covered a decent amount of topics so far. Okay. We've talked about force, and force is going to play a big role in what we're talking about now. And we're looking at work, power, and mechanical advantage, um, and the objects that we can use on a day-to-day basis that helps us manipulate those three concepts. Okay, so we're starting off by looking at work. Work is the transfer of energy to an object by the application of a force. Again, we've talked about forces that causes the object to move in the direction of the force. Now, that is a big statement right there. How do we tell if something has done work on an object in terms of our notion of physics? Okay. If an object moves in the same direction that the force was applied, then work has been done. Okay? So if I push the chair, my force on that chair caused it to move in the same direction that I applied that force. So I did work on that chair. And work can be calculated by, again, this yet another simple formula. Work is equal to force times distance. And it's measured in a unit that we call joule, Joule. Okay? And what joule breaks down to is newtons times meter. So work is equal to taking your force and multiplying by the distance that the object traveled. So when we have non-moving objects, okay, if that force that is applied to an object does not cause any movement into that object, then we say no work has been done. Some examples of when no work is being done. Trying to lift a car. Now, this doesn't apply to me because I do this on the weekends. Lift cars. But normally, when you go try to lift a car, you have to apply a large force. But oftentimes, that car is not going to budge. So there's no movement of that vehicle. Therefore, even though you might feel like you are doing work on it, straining every ounce of your muscles there, that car's not moving. By our definition in physics, no work is being done onto the car. But if you can get that car to move just even the smallest bit, then you've done work because it's measurable distance. Those of you who might be in weights class or who do weightlifting on a normal or somewhat normal basis, okay, when you lift the barbell over your head and you're holding it there, in that instant that you are holding that barbell over your head and just holding it there, no work is being done in that instant, okay? Because that object is stationary, the barbell, over your head, no work is being done. Now, as you are moving the barbell up and down, then yes, work is being done. But if you're just holding an object, like this, if I'm at this instant, I'm just holding my clicker here. No work is being done, even though I'm holding it up. I'm not moving it any distance. There's got to be movement involved. So, steps to calculate. You're going to see this all year long, a page like this. Okay, and they don't necessarily change a whole lot. The only thing that really changes are the types of formula. Steps are generally similar. All right. So as we said, work is measured in joules. And we could break down joules. We could break down joules to two separate levels. Where a joule is equal to 1 Newton times meter, or a Newton meter for short. But we can also break down that statement into what a Newton is. Okay? A Newton is a kilogram times meter per second squared. So if we take kilograms times meters per second squared multiplied by meter again, we get kilograms times meters squared per second squared. And the reason why we tell you how you can break these units down is because you will have to rearrange the formulas to solve for any of those variables. You're going to have to solve for force, you're going to have to solve for distance, and you're going to have to solve for work. So you need to know what units are going to remain once you solve for a various variable. So you will then determine the known values, determine the unknown values, insert the known values into the formula for work, solve them mathematically for whatever you're trying to solve for, and don't forget your units. Okay. Let's do a couple practice problems here. So a crane uses an average force of 5,200 newtons to lift a girder 25 meters high. How much work does the crane do on the girder? Now, because it's really difficult with the program I'm using to see the screen, I'm going to go ahead and just minimize this, and you'll still be able to see it, but I'm going to use the whiteboard up here. Okay, so I'm going to minimize out of here, go here, and do my best to adjust here. And all right, let's go back to the question here. A crane uses an average force of 5,200 newtons to lift a girder 25 meters high. How much work does the crane do on the girder? All right, so the formula again for work is equal to force times distance. Okay, and so what do we know? Okay, we are told that we need to calculate how much work is done. First of all, you want to ask yourself, well, can we even calculate work if there's no movement, if there's no measurable distance? Okay, because if there's no measurable distance, then your work would be zero because of the arrangement of the formula here. So the force in question was 5,200 newtons, correct? Yep. That girder has you need a force of 5,200 newtons to lift the girder, and it travels 25 meters. So when we put these values in to our equation, work is equal to 5,200 newtons times 25 meters. How much work is done? And I'm going to ask you for your input because I don't have a calculator on me right now. 13,000? 130? Ah, thank you. Joules. 130,000 joules. So a decent amount of work. I mean, lifting 5,200 pounds at any distance is a lot. Okay? We go on that one? Because I'm going to erase it. We'll go to the next question. Okay. Number 2. A mechanic uses a hydraulic lift to raise 1,200 kilogram car 0.50 meter off the ground. How much work is done on the car? Okay, so again, we're still solving for work. And we did move it half a meter, so work is done. And so what was our force again? 1,200. And our distance was half a meter. So how much work was done? 600 joules. Perfect. Questions on how we solve work. All right, so moving on. All right. Now we look at power. Because you obviously need power to do work. And you can do work because there is power. Okay? So, we're going to show how they're related. Power is a quantity that measures the rate at which work is done or energy is transformed. So how quickly a job gets done. How quickly an action gets done. So time is our component now, along with work. And so depending on how much time it takes for a certain amount of work to be done, that's going to tell us our power. So power, to solve for it, this time you take work divided by the amount of time in question. And we measure power in watts. Work, again, is in joules. Time is in seconds. So time is a major factor in the amount of power of an object. The shorter the time taken to complete the work, the higher the amount of power. And so, on the flip side, the longer the time to complete the same or a certain task, the less amount of power. The prime example is going upstairs. In terms of work, if you walk up a flight of stairs or if you run up a flight of stairs, doesn't matter. The same amount of work is being done. But in regards to power, since time is a factor, if you walk or if you run up a set of stairs will overall determine a different amount of power between those two scenarios. So walking and running up the stairs, same amount of work, but different amount of power. So the SI unit for power is the watt, as I mentioned. It's a capital W. Okay? And 1 watt is equal to 1 joule per second. So work per second. Now, we got to be careful. I know it's really hard to tell if you do it in your own handwriting. But in physics, when we are talking about variables or units, we use italicized and non-italicized letters to help differentiate because we only have 26 letters in the alphabet. There's a lot of variables and a lot of units out there that need to have a letter representation. Okay. So if you see a non-italicized capital W, that stands for watts. If you see an italicized W, that stands for work. That's how physicists get around with using the same letters to mean different things. Change how they look. All right. So again, steps to calculate power. Write down the formula. P equals capital W divided by T. Determine the known value or values. Determine any unknown values. Once you've done that, insert those known values along with their units into the formula. Solve them mathematically. Again, don't forget to include your units in your final answer. All right. Questions. Then we're going to be done with notes for the day. So Anna walks up the stairs on her way to class. She weighs 565 newtons and the stairs go up 3.25 meters vertically. If Anna climbs the stairs in 12.6 seconds, what is her power output? Okay. So what do we know? I know that I need more room up here. All right. We know that Anna weighs 565 newtons. So I'm just going to jot that down as an F. What did I say it was? 565. 565 newtons. Okay. We also know that she climbs a set of stairs that is 3.25 meters in length, or vertically, I should say. We also know that eventually in A, she climbs the stairs in 12.6 seconds. So that's going to be our time, 12.6 seconds. We need to figure out how much power Anna had during that. But one thing's missing. We can't solve power just yet. Why not? We don't have joules. We don't have work, right?
Pardon the interruption, please. If I could have everyone's attention just for a couple of minutes. Students, first of all, I'd like to say thank you for following the arrows in the hallway. I've been out and about, and you guys are doing awesome.
I'm gonna keep working. Just listen.
I really, really appreciate that. Please keep up that. When we start lunch in just a few minutes, what you will do is report to your lunch zone. I sent an email out the end of last week or the beginning of this week. You should have received it. If you have not looked at that, you need to. But you are assigned to a specific lunch zone. You are either assigned to the cafeteria, to the library, to the hallway near the cafeteria, or the gym. So please look at that if you have not done so, and that is where you report before you ever go to the lunchroom. Students who are eating in the lunchroom will be first in line. I will come to the other lunch zones and dismiss you when it is time for you to go get in line. Thank you. We'll get through this and we'll get better at it each day. Again, thank you for your cooperation.
What do we get here? 0.25. That's going to be joules. Okay. So we now have our work value. So now we can calculate power because it's work divided by time. So take what we calculated, 1,836.25 joules, and divide it by the 12.6 seconds that we saw. And so what do we get for that? $145.7, 145.7, and it's going to be in watts. Now you can put a capital W, or if you want to write watts, that's fine as well. We got a part B here, folks. So hold tight, and then we're gonna be done. Okay. And I don't think I wanted to erase that entire thing. I did not. What is her power output if she climbs the stairs in 10.5 seconds? Now, what's nice about this is we already know what her work was, which I erased. 1,836.25. Wow. Steel trap for an old man. Okay, and that's in joules. And time is 10.5 seconds this time. 0.9. So 174.9 watts. So which is more? The one where it took 10.5 seconds. So shorter amount of time, greater amount of power output. All right. So for tonight's homework, first of all, good job today. I've got your worksheet. Five questions for work, 5 questions for power. You will bring these in tomorrow. Make sure your name gets on these. All right. It's going to take a few more moments. Oops, I need to stop the recording.